Hello, everyone. My name is Marika, and I will be the moderator of today's meetup. First of all, I want to thank you, everyone who joined already. As we are waiting for more people to join, we will be waiting for 5 more minutes, and after that, we will start. So I see people joining, but until we start, I also want to tell the rules of the meetup and tell a little bit about our company. So, hello again, when you joined. My name is Marika, and I'm the moderator of today's meetup. And until we start, we will talk about the rules of our meetup. So during the talk, you can ask questions via Zoom chat. Please check that your questions are visible for everyone and that all participants can see them. And after report, the speaker will answer this question. At the end, you also have opportunity to unmute and ask your questions in English, so our speaker can answer them. And recording of the meetup will be shared with all registered participants in 1-2 days after the meetup. Also, while we are waiting, we want to tell you a little bit about Grid Dynamics. I hope most of you know about our company, but anyways. So let's talk about Grid Dynamics. Grid Dynamics is a leading provider of technology, consulting, engineering, and data science services for Fortune 1000 corporations from financial, technological, and retail sectors. It has been operating since 2006 and headquartered in California and has development centers in United States, Eastern, and Central Europe. So here you can see our offices around the globe. There's more than 4,500 employees all over the world that are working at Grid Dynamics. So as for today, Grid Dynamics brings together more than 4,000 engineers in 18 countries. Also here you can see technology innovation partners that we are working with. I think that most of these companies are very known and you know them. And here you can see technical partnerships that support our clients. Also, if you want to know more about our company or check opportunities in your area, you can go to our career website and check the information. It's updating there. And you always can send the CV if you're interested to our recruitment team. So for now, I see that people is joining right now also. But I will present our speaker. So Dmitry Mezhensky will be our speaker today. It's our big data architect at Grid Dynamics with the topic data engineering transformation in Gen AI era. So Dmitry, I think that we can switch the screens. I will stop sharing.
All right.
And you can share your screen and I will give you a virtual microphone so you can start your presentation.
All right, you should be able to see my screen.
Yes, now we see your screen.
All right. Thanks a lot, Marika. I'm glad to talk today, Dynamic Talk. Thank you all guys for joining this session. I see lots of people joining. Feel free to ask questions in the chat. I'll be making pauses and going through the chat, answering your questions. And we have time at the end of the presentation to talk about different aspects of data engineering and generative AI era. So for today, our plan would be to start with a general overview of how traditional data engineering looks like. It's a well-known thing. I'm pretty sure you know that. And the idea is to recap and see what changed for the last 2 years. What are the major areas of impact, where you should put more focus, and where challenges are coming from. And obviously, to discuss it in detail, we need to discuss briefly how Gen AI evolution looks like. What is ROC? What is happening there? And what AI expects from data engineering. And then we'll jump straight into data engineering. We'll discuss how we are doing data ingestion right at the moment, how we are preparing the data, what are essential details of preparing the data, how we are check consistency, how we do observability of overall data pipelines. And here, while we will be talking about observability, we will also touch observability in general, including large language model observability. And when we will be talking about it, I'll be mentioning modern tools and technologies which we are leveraging at Grid for this purpose. And feel free to ask questions. All these tools are very new and very emerging. So we don't have industry standard tool set like we have for data engineering at the moment. That's why please don't surprised and please share an opinion if you have any. With this being said, let me turn over to our view of traditional data engineering. So as you all know, it starts with data ingestion, and we have lots of data. And this data in traditional data engineering, in predominant amount of use cases, is structured. So we have data coming from databases. It might be transactional databases like Oracle, which handles lots of transactions and from which we are getting sales information. We might have other operational stores, or we have still on-premise databases, data warehouses like Teradata, which are about to be decommissioned, and we already have all the required footprint of the same technologies, I mean, the same logic in the cloud. So once the data is ingested, usually we have lots of pipelines for that. And these pipelines are orchestrated. We also apply data quality rules on top of it. Usually it's rule-based approach. And we all provide access layer to the data whenever data resides. It might reside in data lake, it might reside in data warehouse, but still we'll be providing access layer for the data for business users, applications, engineering, analysts, and so on. And we might have data governance on top. So we have plenty of consumers, but our rules are strictly defined. Structured inside, structured in, structured out, and we might support dozens of data sources at the same time. Some of them might be streaming through Kafka or maybe Redpanda and others. And this is very well-known thing. So it's already became a commodity, and on the market you might find lots of successful stories how one can build scalable data platform. But since starting era of Gen AI, we have new demands and new expectations from the data. And initially, these demands started with machine learning. So machine learning brought new features to the table. You cannot just prepare data and call it golden data layer, and anybody across the company can consume this data. Now you should be able and should be flexible, obviously, to help data science team to prepare data sets for them, so-called feature data sets. And those feature data sets are relatively different from usual pipelines. You need to prepare them fast. Sometimes you need to support various real-time scenarios where you need to load required features on the fly. And this was just one of the first bells ringing in the industry that data engineering is changing, and we need to have new approaches for that. And since then, once the generative AI evolution started, it's initially started with, first of all, deep learning models and generative models. And deep learning models required specific data processing. And now it's no longer just structured data, which is very clear how to use, how to transform, how to store. But now we might have also images, video, audio, or unstructured text. And due to that, we need to extend our capabilities and start processing images, start processing video. We need to have an idea how we will be storing images, all these types of unstructured data. And moreover, sometimes we need to normalize it. If we have images of different resolution, we need to apply it or need to normalize to just one resolution before we are doing any training or inference. And this is just of the one of the points out of dozens which we need to consider in our pipelines. But since then, large language models appeared, and large language models, generative models, changed it drastically. So let me start with the overview of very simple retrieval augmented generation architecture. And this will be very helpful for us to get an idea how data engineering is transforming at the moment and what are the demands. Usually, and let's take as an example that we need to build a knowledge-based system in the organization which can process PDF files, presentations, Word documents, Excel files, and we need to build semantic search on top of that. So that if I need to find a document with a specific content, I can just type in corporate search system, please find revenue documents from 2024 second quarter. And they should be able to find all documents which semantically similar to this request or contain this information inside. For this, we need to ingest all the documents, and all the documents can be just simply stored as is. They need to be chunked and then vectorized. So this vectorization process is called embeddings creation. And there are plenty of algorithms how we can create these embeddings. And this is mostly up to AI engineers to define how these embeddings should be created, specific algorithms and specific vector search databases that they would like to use. And once we take all the documents, splitting them into chunks, and we need to split them into chunks just because each LLM model has limit on their context size, and we can't just simply take a document of any size and feed it into the LLM. So this is why we need to make these embeddings. And the problem is that if we are making embeddings, we need to split documents meaningfully, so that we need to identify either sections so that we can store meaningful parts of documents without abrupting them in the middle or close to the end, and then store them in a vector database. On top of that, there are different techniques how once a user files a query, and this query is also passed through query reformulation, and then to embedding model to create embeddings, another vector which will be searched in a vector store. And then once we find relevant documents, we again need to use an LLM to generate the answer, to rate it, to make semantic, to choose several documents out of all search results, which are semantically similar to what we're looking for. And this is RAG architecture. And you might question, why do we discuss in our data engineering session RAG, which is not directly connected with data engineering? And the case is that usually the left part of the of this architecture, it's up to data engineering. And RAG architectures are relatively different one from another. And the problem is that it's not very obvious where responsibility of data engineering ends and AI engineers are starting their work. And those gray areas might introduce extra hallucinations in the system when our RAG can behave unpredictably. And this might be due to quality of the data. And those challenges usually are due to either complex data structures which are not prepared properly, or improper chunking, which we just discussed. Or it might be that even though chunking is okay, but still embedding model and vectorization algorithms that you're running are not fully accurate. And lots of other issues as well. And here, AI engineers, while they will be investigating challenges with RAG and trying to optimize search, semantic search, they will need full support from data engineering, and expectation from data engineering is to help with creating various projections of data, trying different algorithms, keeping in sync data across multiple systems, and we will talk later on what's challenging out there. And then keeping track of actually managing data lifecycle in the whole application, the whole solution, so that AI engineers can focus on their particular tasks. And these are usual ways how RAG applications can be tuned, and these are very basic steps. And some of you who are already running RAG systems know that there are much more advanced techniques, but we are not talking about them at the moment. We want to bring focus to data engineering and see what are the dependent parties and how we can simplify and streamline the development. And we'll start our journey with understanding with data preparation. Then we'll talk about what is the area of responsibility, and we'll briefly touch various technologies as well. So this is the next section, and before moving on, let me make a pause and look through the chat to see if you have any questions so far. Right?
I think not on this step.
All right. Thank you, Marika. And let's start with unstructured data processing. As we already mentioned, we have images, videos, audios. We might have PDFs, Excel files, and obviously we'll have a portion of structured data as well. And we need to build data ingestion in the way that it's generic enough to plug and play with various data sources. We might have not only data coming from file system, distributed file system. If we're talking about AWS, it might be AWS S3 for storing images or video, and for data warehouse, let it be Snowflake. But currently at the moment, since RAG systems are evolutioning very fast, we might also need data from systems like SAP, Salesforce, and many other commercial systems which are previously were not used at all. And due to that, the system which will be ingestion layer which we'll be building needs to be very flexible and support various types of data sources. And now when it comes to data indexing, as we already discussed on this step, this is major step of the quality of the entire solution. If we do everything right here, it means that the whole system won't have extra sources of hallucinations. Otherwise, it will be relatively challenging to identify where some hallucinations are coming from. And now, as we can see, we have entire system, and this entire system usually consists of data warehouse, some structured data source, other databases, then ingestion layer, then some intermediate layer for indexing purposes, and then vector databases, feature stores, cache layers, and so on. So there are a lot of layers through which data is traveling, and if our pipelines are, due to any reason, failing in between, or we are not updating whole data sets, but just updating part of it, it might introduce very hardly issues which are very hard to identify and track. And moreover, in modern orchestration, there are different approaches how industry wants to address it. First of all, usually many of you who are doing data engineering on a daily basis are familiar with technologies like Apache Airflow, Prefect, or cloud-based solutions like Composer, or similar to that, or maybe, let's say, AWS pipelines. But the thing is that in industry, there is a well-known tool developed for machine learning pipelines, which is Dagster. And I mentioned it on the orchestration box. And also, nowadays, we have Temporal. This is a startup which is developing. I can't say that they don't name themselves and just an orchestration tool. They name the platform as a platform which can orchestrate different business processes with a focus on AI agents. And they are growing very fast. Still, not many production installations as other competitors have, like Dagster or Apache Airflow. But they want to replace existing players on the market. And their idea is to simplify workflow orchestration and introduce dynamic workflows. In comparison to Airflow, there is DAC, which is not changing during runtime. You can also introduce dynamic DACs inside to change it during runtime, but this is a kind of anti-pattern. And temporal is a natural thing how you can react on events and build a more flexible event-driven system. So this is still something that we observe on the market. And I can't say that it's stable enough, but very promising, and maybe would be one of the tools going in the future. And generally, the idea here during unstructured data processing is very simple and straightforward. We need to make very transparent pipelines, ensure that data in source and target are in sync. All transformations which are building here on a data indexing layer while we are creating embeddings should be done with some level of testing. Ideally, it should be fully automated testing, which allows you to validate the output and check that all the embeddings are creating accurately. And then you check that they all are delivered to the system. When it comes to loading data, usually it's massive amounts of data. And if we are doing it in parallel, we should track any failures to avoid that we loaded 95%, but 5% is missing out there. So this is step of unstructured data process. And now let's move on to data vectorization. So this is step which is not your full responsibility if you are data engineers. And idea here is very simple. You start with data preparation. You are well aware of it. It's create structured format when it's possible, remove duplicates, try to eliminate data with missing values if it's possible. And on top of that, you are creating features, you are scaling the data. It might be changing resolution of images if it's required, or applying same resolution for all images. It might be that you are chunking videos or taking meaningful frames out of it. And if you are doing that, obviously, to get an idea of what is meaningful, you need to use LLMs for that as well. So this is data preparation step. And after that, together with AI engineers, you're usually working on data chunking techniques and strategies. And I won't be going very deep into it since it's quite complex topic, and it might be a separate session dedicated just to data vectorization. But a few insights out of it. You can use, again, LLM for chunking to build context-aware segmentation so that you don't split the context into separate chunks. You need to change dimension sometime if it's required. And after that, you vectorize the data, and vectorization is very different from project to project, the way I see it in grid dynamics. That's why I would say it might be completely different. And at a very high level, it's just identifying algorithms which are working, vectorize it, test it, load, test everything end to end, then create tests, synthetic tests to validate that your search is working accurately, and then validate how this all the system functioning. Now, and this is very vital part of our conversation. This is about how we ensure consistency. This is exactly the same naive rock architecture with few simplifications, but with focus on gray areas. We have our ingestion pipelines, which are ingesting data. Then we are doing chunking, the vectorization, and store the data. And usually you might consider that, okay, this is the end of our responsibility, all is fine, and we don't need to do anything on top of that. So we delivered the data, all good, and now AI engineers should start playing their role in creating target solution. And the thing is that here we might have stale data. We might have the case that source changes, but we don't know how to validate whether source changed and do we need to update it in target. We might have the case that here on this architecture, we have just vector database, but we might have also caches as well. And we need to update data consistently in vector database and in cache as well. We might have the case that we are not just updating the cache and it stays immutable throughout life cycle, but applications are updating cache as well. For instance, we are loading embeddings to cache, which is improving semantic search. But then applications in real time, if they can create better embeddings, are updating it in cache. And we need to track it. We need to offload such embeddings and use it for investigation later on. And this breaks consistency. So the farther you go, the more nuances you will start investigating. And this is exactly the point where these gray areas appear. So you start very simple, but then you need to understand who is in charge of the data in cache, which is constantly changing by multiple applications, which might find better prompts while they are working. In this case, and this is a question to the entire industry, usually the answer is that it's data engineering still, even though it's runtime cache of application layer. It might be partial data engineering, it might be joint responsibility, but at the end of the day, you will need to track these changes, upload them somewhere, and then do the comparison to see what can be improved the entire system, and then apply to vectorization pipelines. And this is the case of data being not in synchronization. In this case, you need to think how you will be dealing with it. Whether it will be changing some business logic or whether not, and how you would like to deal with it. So these are main gray areas that might appear at the beginning of introducing RAG applications and AI agents. As you go, you might also need to cache to optimize the whole system and cache requests to LLMs, then work with this cache effectively, keep the most trending requests to it. It might be not already data engineering responsibility, since it will be just operational cache, which is used to reduce queries to LLM, but still will be a vital part of the entire system. So let me make a pause if there are any questions. Let me see through the chat. Right, I see the question,
Yeah,
how do
we
you
have a
work?
lot of questions now,
Yeah.
but you can answer them in the end if you want.
Let me see if I can answer and right at the moment. So the question is from Simon. I will be covering the tools that you commonly use for these different types of data preparation. So for data preparation, we are using mostly orchestrators like Apache Airflow, Dagster, and we use traditional applications written on top of Apache Spark or Flink for that. Or sometimes we can use just lambdas, which are making changes, granular changes of the data, if it's possible. And we are exploring other technologies, like I mentioned, temporal, which might be very helpful, but still, for us, it's not running in production. In the context of important aspect is re-ranking or any insights about it? Thanks. Yeah, re-ranking is important aspect, but in case of this data engineering session, we won't be covering that much. It deserves its own session where we'll be discussing the various vectorization techniques, ranking, and optimizations that we can bring on top. So it will be out of the scope today, sorry. And next question, again from Simon, how do you work out whether to use more traditional TF, IDF versus vector indexing? So for us, it's up to AI engineers to identify what algorithms work better. And today, again, it's out of the scope because it's very specifically focused on the way how data is vectorized. And the last one from Vladan about experience with MongoDB Atlas Vector Search. We'll be talking about it and a few other options close to the end of the session.
Thank you.
Okay, so moving on. Next step is observability. And here, I cannot just separate observability, data observability from LM observability. It will go side by side. And usually it starts with identifying your data at the very beginning so that you see what data you have for the input. And ideally, you should have data drift metrics defined on top of your data sources so that if your data starts drifting, you at least have an idea and you can make any projections how it might affect the output. Then traditional data engineering validations, observability, and data completeness is a must-have, but you are all aware of it, so we'll skip it. In data pipelines, while we are creating embeddings, it would be very beneficial to have a kind of smoke test validation of these embeddings, ensure if your embeddings are created properly. And on this step, someone might introduce data tokenization as well. The case is very simple. You have lots of PI data. You need to mask your emails, commercial information, whatsoever, so that your data is not going outside, especially when you are using public Gen AI services like OpenAI, and you want to create vectors, pass those vectors to the model and do the ranking with all these data masked. This means that you need to run tokenization, and due to that, you again need to validate the data and check that your masking strategies are applied as you expected, and vectorized data doesn't contain any sensitive information. And then finally, the end-to-end synchronization should be checked, starting from vector database up to the cache layer if you have any, and then tracking information about any validations, obviously performance, and consistency checks if you can apply any. And at this step, you might use a very wide range of technologies, starting with well-known open source, evidently, open source version, and they have commercial version, up to commercial products like weights and biases and rise. They all have tool sets for just simple validations and observability and track observability as well. So you can also apply observability metrics not only for data, but for the entire RAG applications. And we won't be going deeply into it just because it's, again, deserves another session talking about how observability should be implemented for a particular RAG system. And another topic which is deserves also to be mentioned in this session is cost tracking. We have various, we might have multiple applications which are using LLMs, and if we're using public services, we need to track it properly. For that, you can use LangFuse, you can use your own monitoring systems, and the case is that you need to track it properly and have an idea how much money a single request might cost. In our case, just recently, we're building an AI agent which optimizes a SQL query, and it turned out that 5-10 consequent requests to OpenAI might cost up to 20-30 cents, and it's extremely expensive when we are building a system which is optimizing SQL queries for business users. Keep in mind that we might have hundreds or maybe thousands of business users using this service, and it might be too costly for the organization to pay just for a single service. And that's why cost control is one of the major points that the entire observability system should have, even though it's not directly connected with data engineering, as you might think. And so these are like general responsibilities nowadays of data engineering, the data engineer, and skills that someone expects when it comes to build RAG systems or AI agents. And as a summary, I wanted to give some insights of using using different vector databases, and maybe have some short discussion, or you can share experience of leveraging various vector databases or challenges that you faced. For us, we tried different vector databases like VV8, cloud, native services coming with Vertex AI, and nowadays even BigQuery, Google BigQuery provides vector search for the data in data warehouse, in BigQuery data warehouse. So it seems now that it seems to be quite good product. We like VV8 and we use it in some of our projects. And for other aspects, Quadrant is also good, but VV8 has various searching algorithms. It supports high-dimensional vectors, and it has lots of connections to other data sources, making it relatively easy to load the data and transform it. So this is it. And in terms of general challenges, I would say that, as we discussed, new approaches to ingest data, support AI engineers in vectorization, keep synchronization of the data and make it automated if it's possible, and one-stop observability, which will save lots of time for you while your data is making a journey in the system. So let me see. I see yet another question. How do you calculate, track efficacy of different models, impact of different prompts? For instance, quality metrics one from output. So this is the question that usually AI engineers are taking. For us, we are creating robust data pipelines, deliver data, and deliver infrastructure. That's why I would love to involve AI engineers to answer this question. And I see that on Vertex, you're saying that you're looking into ways retail, more of alcohol alternative. So yeah, this is outside of our data engineering responsibility, so cannot say much about it. Thank you for the question, Simon. So, and in terms of gray areas, as we mentioned, it's not obvious what is the exact scope of responsibility for modern data engineering. Previously, once you deliver data to golden layer, create data marts in data warehouse, or create data products in data lake house architecture, it was the end of the responsibility, and then consumers were consuming the data and using it at their disposal. But at the moment, various systems and dynamic nature of changing the data makes it much more challenging to support it and to ensure that it stays consistent throughout the whole journey. So that's it that I wanted to cover today. Any other questions that you like me to focus on?
Dmitry, first of all, thank you so much for this interesting speech. So all attendees can ask questions in the chat if you have any additional questions. And if someone wants, you can unmute. Also raise a hand, unmute, and ask question by voice if needed. Mikhail raised a hand. Yes, Mikhail, you can ask the question.
Thank you so much for interesting presentation. I have maybe not typical question, but in few projects, when our customers are waiting for us for forecasting some kind of demand forecasting, we have faced situations when data complexity was not fulfilled tooling which provide enough accuracy. So, for example, too rare data set, not enough inputs in data set, or not enough dependencies in data set. So, how do you think? Is there any tooling or approaches which could? I think there are two questions. Yeah. At first, to discover it faster, then we do it during traditional EDA approach, or to find the better way to overcome it. That's it.
Mm-hmm. Yeah, thank you very much for the question. Yeah, so the case is that sometimes on the ingestion phase, while you're ingesting the data, you might see that the data distribution, data volume might change. And data observability greatly helps here In Grid Dynamics, we developed our own custom solution for that. I can send a link just so you can see the video of it. And there are plenty of the tools available on the market for that. For instance, Soda Core, which comes on top of my head, provides it so that you can build observability metrics and check data distribution, any statistical metrics, which will give you an idea that your data is sparse and you need to stop the pipeline and to make an investigation. And your second part of the question, how to fix it or how to deal with it. If you have control over upstream dependencies, then you can build more advanced observability scenario where you can see what is the root cause analysis, fix it, and play the data. But if you have no means of control, then most probably you will just raise the issue and that's it. And you will have to wait until it's fixed upstream, and then you can re-ingest the data.
Okay, thank you so much. Yeah,
Yeah,
will be great.
thank you.
Mhm.
Thank you. And I see yet another question.
Yes, in the chat.
Yeah. Any thoughts about platform independent solution? For instance, like Dockerization from a data engineering point of view. Let me make a clarification. Platform independent solution in terms of what when we're talking about data engineering, because data engineering is complicated thing and contains out of many about cloud platform. So if you would like to be cloud agnostic for your data engineering, right? So that you are okay, yeah. So what is independent solution for data engineering, which is cloud agnostic from cloud providers like AWS, Azure, or GCP? Great question. We have a couple of clients who would like to stay completely agnostic from the underlying hyperscaler. They have their on-premise data center, but also they want to build, since they are running out of the capacity, they want to build solutions in the cloud and leverage cloud hardware, but still be agnostic. And in this case, your friends are, first of all, Kubernetes, and you can use it for running distributed compute, like Spark supports, Apache Spark supports Kubernetes. You can run Lambda services like AWS Lambda on top of it for very small chunk processing, again on top of Kubernetes. For distributed data storage, you can use Ceph, and this is proven technology which is used as object store. For data warehouses, there are several recommendations on the market. I won't be going very deep into it. You can use solutions like ClickHouse, but it's not working very well with joins. You can use Apache, not Druid, but I forgot the name. It's Apache product which provides data warehouse, but sorry, I forgot it. I'll see it and try to send it as a follow-up. So this will be your data warehouse. For lakehouse architecture, you can build on top of your object store solutions like Databricks, Data Lake, open source version, or Iceberg or Hoodie, which will be providing you some sort of lakehouse capabilities on top of. And Apache Beam is just another framework which provides distributed computations. But I was referring to data warehouse that is developed under Apache Foundation. And it's to your question, Christian. Remark to your question. And on top of that, you can run for orchestration anything that you would like, starting with traditional Apache Airflow up to any other modern solution. It will work perfectly fine in Kubernetes. If you'd like to run Apache Kafka or maybe Red Panda or anything else, again, it will be running fine on top of Kubernetes. And this architecture can be scaled well on different hyperscalers, but you have to deal with several key aspects. First one, how you will be managing permissions, some sort of identity access management in this solution. And it's a very sophisticated thing. You need to have synchronization with your LDAP or so whatsoever you're using. You will need to implement something for monitoring or use commercial products for that. So this is a very sophisticated solution. It costs lots of money and is built by large organizations who would like to stay agnostic from cloud providers and have an ability to easily migrate from one to another. But this is the direction which usually such companies starting from to build such type of platforms.
Okay, any other questions? I think that that's it for now. Dmitry, thank you so much for your talk. It was very interesting. We had a lot of questions and discussion. Thank all attendees for coming to our meetup. We are very glad to see you, and we will see you again, I hope, on our next Dynamic Talks. So I wish all of you a good day or evening, and bye.
Thank you. Have a
Thank
very
you so
good
much.
day. Bye.
Thank you. Bye-bye.